permutations that have at least, at most, or exactly, or none. Okay, so student council example again. The student council decides to form a subcommittee of 5 council members to look at how blah blah blah, doesn't matter. Okay, there are a total of 11 student council members, 5 are male, 6 are female. See you, girl. How many different ways can this subcommittee consist of exactly 3 females? Well, how many females do we have?
6.
6. We need 3 of them. Okay, but the subcommittee consists of 5 total members. So if we have exactly 3 females, we need to multiply by our selections of males as well. We started with 5 males. If we've already used 3 out of 5, that means we only need to choose 2 more. Okay, because there's 5 council members. We just have to multiply that through.
What's that equal, Brett?
Brett's my checker.
Let's go.
You got it, 200.
200.
There you go, PF.
0.
So 200 different ways we can have exactly 3 females and 2 males. Okay, at least 3 females. That means there's going to be a few different scenarios that we consider, and there's going to be or scenarios. Please pay attention, right?
6. Choose.
All right.
3.
So one scenario would be that we have 1 female and 4 males. Oh no, sorry. We need at least, not at most. Okay, so if it's at least 3 females, we need 3 females and then 2 males. Or we need 4 females and 1 male. Or 5 females and 0 males.
You have no.
The or means add. So if we have 3 females, it's pretty much, and 2 males, it's exactly what we had here. Okay, it's 6 females, choose 3, times 5 males, choose 2. Okay, the next scenario is if we had 4 females, so we'd have 6, choose 4, times 5, choose 1. And lastly, 5 females would be 6, choose 5, and 5, choose 0. So we have 200 plus 75 plus 6, 281. Now, if we had at least 1 female, we could use the same process we just did here. We would have 1 female, 4 males, 2 females, 3 males, etc., etc., etc. Or we could short track this solution a little bit. Basically, we could calculate if there were no restrictions on females, minus the scenario, that's the non-example, that would be no females. So if we take out that possibility of no females, that means all the other options will be at least 1 female. Okay? So for no restrictions, how many people do we have in total? 11. And the subcommittee needs 5. So we have 11, choose 5. We're going to subtract the scenario if there's no females. So of the 6 females, we are going to choose 0 of them. And of the 5 males, we're going to choose all 5 of them. So 11 choose 5 minus 5 choose 5, 6 choose 0. She got 462 minus 1. We got 461. Okay, so you could have solved this problem as well as we did in part B, but that means you're adding 5 different scenarios together. Okay. So this is just a little bit shorter if you consider that non-example. Alright, back to our cards. So we still have a standard deck of cards, 52 cards in the deck. How many different 5-card hands can be formed containing at least one red card? Do you guys want to do the or scenario or just restrictions minus the non-case? A little bit shorter, eh? So no restrictions. Minus no red. Or all black. So no restrictions would be 52 cards, choose 5. No reds would be 26, choose 0. Multiplied by 26, choose 5. Now why am I multiplying by that? Because this is 5 black, and this is 0 reds. So we're taking out the scenario if we did have 0 reds. So 52 choose 5 minus the right hand side of that. Lots of possibilities. 2,533,180. Alright, at most 2 kings. That means we could have 0 king and 5, K bar I'll just say is non-kings, okay? So it's a card that isn't a king. Okay, so one scenario is 0 kings with 5 non-kings, or we could have 1 king and 4 non-kings, or we could have 2 kings at most and 3 non-kings. Maybe I should put or instead of plus signs for the start. Okay, so for 0 kings, that means we have 4 kings in the deck, but we're going to choose 0 of them. If we are excluding the kings, I have 48 cards left. I need to choose 5 of them. Or, which means add. Of the 4 kings, we're going to choose 1. And of the 48 cards left, we're going to choose 4. Or, of the 4 kings in the deck, we're going to choose 2 of them. Multiply that by the 48 cards that were left, we're going to choose 3 of them. Alright, so that should be 2,594,400. Brad's testing it, I like it.
Did you not like you have gone to Scotiabank for a while and not CC?
Alright, last scenario, we have exactly 2 pairs. So a pair is when we have the same card twice, or same number twice. So for example, if you had a 3 and a 3, or an 8 and an 8, that would be 2 pairs. So in each suit, we have 13 numbers. Okay, in order to make a pair of those suits, in order to make 2 pairs, we need to choose 2 of those numbers. So for example, we have 8, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. Okay, that's 13 different cards for every suit. In order to make 2 pairs, we would have to pick maybe a 6, let's say, and let's just do something small. Okay, a 2, right? So we would pick in order to make two pairs, we need to pick two different numbers. So one pair would be a 2 and a 2, and the other pair would be a 6, 6, and then we would have some other card. So in order to show that we have picked the 2 and the 6, of those 13 cards, we would go 13, choose two numbers. Okay, so for the last one, to have exactly two pairs, we have to start by first picking what two numbers will make up those pairs. Okay, but for each number, say for 2, how many 2s are in a deck? 4. So we would have to multiply by 4, choose 2 of them. So we only need 2 of the 2s to make a pair, or 2 of the 6s to make a pair. So that's for our first pair. Okay, let's say it's for the 2s. For our second pair, which was the 6s, how many 6s do we have in a deck? 4. We need to choose 2 of them. So right now, I have selected 4 cards from the deck. Okay. So I need one more.
Did you already, like, in the first one though, haven't you already selected 2 cards?
So I've selected the number, but I haven't actually selected the cards yet. So it's like, out of 13 numbers, I've selected 2, but I haven't actually taken the cards yet.
Oh, okay.
Of the 4 2s, I now take 2, and then of the 4 6s, I'm going to now take 2. Okay, so if I were to take the 2s and the 6s now out of the deck, how many cards have I taken out of the deck? 8. So 52 less 8, that gives you 44 cards left, and we only need one more to make a 5-card hand. So I just put a little note for that 44. We had to go 52 minus 8 cards, and the 8 cards came from the 2 numbers in the deck. So the 2 numbers that made our pair. Okay, so now we just have to figure out all these combinations, multiply them together, and you should get 123,552. So now we're going to look at when we have combinations that are equivalent. Fran and Bernie have identical collections of vintage toy vehicles. Fran selects 2 toys from the 10 shown for a display in her cabinet. Since the order of the display does not matter, she calculates that this can be done by taking the 10 toys and choosing 2 of them. Okay, and if you calculate that, there's 45 ways in which you could choose these 2 toys. Okay, I'm just going to pick these 2. Motorbike, yeah, this is a pretty cool truck too. Okay, so I've selected 2 of the 10 toys. Now Bernie selects 8 toys from the 10 shown for display in his cabinet. Since the order of the display doesn't matter, he then calculates 10 choose 8, or 45 ways. They're equivalent. Okay, so I'll just pick these ones for Bernie. So explain in words why 10 choose 2 is equal to 10 choose 8. Any guesses? Basically, selecting 8 is the same thing as not choosing 2. Okay, or selecting 2 is the same thing as not choosing 8. So selecting 2 toys is the same as not selecting 8. Okay, now using factorial notation. So just a reminder, using the formula for combinations, it's n choose r. That would be n factorial over n minus r factorial times r factorial. Okay, so for 10 choose 2 on the left hand side, our n is 10 and our r is 2. So we would have 10 factorial. Maybe let's write out 10 choose 2 first. Okay, 10 choose 2 equals 10 factorial divided by 10 minus 2, so that's 8 factorial, times 2 factorial. And 10 choose 8 would be 10 factorial divided by n minus r, so 10 minus 8 factorial, which is 2 factorial, times 8 factorial. Same. Quite different. So let's just give another few examples of equivalent combinations. Okay, you can talk in terms of toys, describe it, or you can use a combination. I'm going to put it up to you guys. Okay, any examples where you have an equivalent combination?
It's 10C3 and 10C7.
10C3 is equal to 10C7. Perfect. Okay. Or we could do 12 choose 4 is equal to 12 choose 8. Basically, as long as the numbers of R that are taken at a time add up to how many elements you had, they're equivalent. Okay, so general rule. Okay, NCR is the same thing as NCN minus R. Okay, so just as we saw here what Booker told us, so 10C7, that's the same as 10C, and then 10 minus 7 is 3. Simplify that. Alright, so on the left hand side, I showed the formula already, but that's n factorial divided by n minus r factorial times r factorial. On the right hand side, we would have n factorial divided by n minus r factorial times n minus r factorial. I'm just going to keep going with this right hand side, okay? I'm just going to separate that right hand side. Okay, I now have n factorial divided by, well, n minus n is 0. Okay, and then I have negative times negative, positive r, times n minus r factorial. Is this not now the same as our left-hand side? Identical. So we're just using factorial notation. Alright, next one. During a Pee Wee hockey tryout, all of the players met on the ice after the last practice and shook hands with each other. How nice. Algebraically, let's determine the number of players who attended tryouts if there were 300 handshakes. Alright. So if we were to think about handshakes, how many people do you need to make a handshake? Two. Okay, so we're going to have some number of people choosing 2 people to to make a handshake. That's going to equal 300. Okay, because there's 300 handshakes in total. So using the formula NCR equals n factorial over n minus r factorial times r factorial, we're going to break this down and solve for the n. Okay, so our n is n, our r is 2. So we have n factorial divided by n minus 2 factorial times 2 factorial equals 300. Okay, do you guys remember how to break down a factorial? We just have to multiply by the one less than it. So n factorial can actually be written as n times n minus 1 times n minus 2. And I'm going to stop there and put a factorial because in the denominator I have an n minus 2 factorial. Okay, so those n minus 2 factorials can cancel out. Sorry for zigzagging so much. We now have n times n minus 1 over 2 factorial equals 300. What can I do with that 2 factorial? Just expand it, and then we're going to multiply it. So 2 factorial is just 2, because it's 2 times 1, right? So I'm going to just get rid of that factorial. We're going to multiply it by 300. So we have n times n minus 1 equals 600. Expand the left-hand side, we'll get n squared minus n. Move the 600 to the left-hand side. And that equals 0. Then we just have to factor and solve. We need 2 numbers that multiply to negative 600 but add to negative 1. So let's just start putting numbers together. So test it out. Just keep in mind, guys, the 2 numbers have to be 1 apart, because you have to add to a negative 1. 20 times 30 is 600, right? So it's got to be somewhere in between 20 and 30. So just start closing the gap. Right? Excellent. 24 and 25. And if it has to equal negative 1, we'll have n minus 25 times n plus 24. When we pull these out of the factors, we get n equals 25 and n equals negative 24. Can we have negative 24 people in this scenario? No, so that's gone. Okay, that means n is 25. We have 25 people. Yeah. Okay, we can also apply combinations to polygons and diagonals. It's amazing what people discovered, hey? So we're going to consider circles with 5 points marked on a circumference. How many triangles can be formed using these 5 points? Write the answer in combination notation. So if you guys wanted to sit there for a while, you could try and make different combinations of triangles. Or we know there's 5 points. We need to choose 3 of them to make a triangle. Order doesn't matter. So when you multiply that out, you'll get 10 different ways. Okay, next, are you guys okay for the first one? Okay, next one, how many lines can be drawn connecting 2 points on the circle? How many points do we have? How many points do we need to make a line? So we're just going to do 5, choose 2. Are these going to be equivalent? Yeah. We have NCR is equal to NC n minus R. Okay, this will also equal 10. Alright, now we're going to sketch a regular pentagon. Regular means all sides are equal. Pentagon, there's 5 vertices. How many lines can be drawn connecting 2 points on the pentagon, including the sides of the pentagon? How are you thinking about it? You just trying to count?
Yeah, well, isn't it the same as a circle?
So how many lines can be drawn connecting 2 points on the pentagon, including the sides of the pentagon?
This wasn't like including the dots kind of there, yeah.
So again, we have 5 dots. We need to connect with 2 dots. So there's 10 ways.
Plus 5. Or
Plus the sides there. I don't know.
Why are you adding 5?
Oh, I know.
well, I'm asking because it says including the sides.
Well, it's still 2 points, right?
I guess that makes sense.
Oh, that would be included.
Yeah.
Okay.
So I guess if these weren't here, would that change your perspective?
Yeah.
Is it not still the same as this?
Yeah.
Now, how many lines can be drawn connecting 2 points on the pentagon, including the sides of the pentagon? Oh, we just did that one, didn't we?
Oh.
Yeah, sorry. Part 2. How many of these lines are diagonals of the pentagon? I'm just going to draw these out for you. Okay, so we have 1, 2, 3, 4, 5. Make a nice little star. Okay, so 5 lines are diagonals. And basically we're going 5, choose 2, minus 5 in this case. And the reason, are you guys wondering why I subtracted this 5?
Yeah.
So it's number of lines that connect the dots. So I'll just draw a pentagon again. We have 1, 2, 3, 4, 5. So we have 5 lines on the outside, right?
Yeah.
So we're just subtracting those. In other words, we're subtracting on outside. So not diagonal lines. We're subtracting the number of dots. Okay, so if we were to express this in terms of combinations, where am I at? I pretty much just described it. Basically, it's what we had in part I minus the number of sides, so number of lines on the outside. Okay, so it would be n choose 2, and then we're subtracting number of sides. Okay, which could also be like number of dots. So now let's take a look at an octagon. How many dots are in an octagon? Or sides? Okay, there's 8. Okay, so we would have 8, choose 2, and then we have to subtract the number of sides. Okay, and I already developed the rule for you, but it would be for a regular n-sided polygon, it would be n, choose 2, and then you just subtract the n value. So for example number 5, they're not giving us how many sides there are. They're telling us that we have 65 diagonals. So in other words, n choose 2 or minus n equals 65. So we're gonna have to put this in factorial notation first. So we have n factorial divided by n minus 2 factorial times 2 factorial minus n equals 65. N factorial can be expanded to n times n minus 1 times n minus 2 factorial. And we see that the n minus 2 factorials will cancel out. And don't forget we had minus n equals 65. So I'll just clean things up. We now have n times n minus 1 divided by 2 factorial, which is really just like 2, minus n equals 65. So to get rid of the 2 in the denominator, we could just multiply every single term by 2. And these 2's cancel out. So now we have n squared minus n minus 2n. This is 130, so we just have to subtract the 130. So n squared minus 3n minus 130 equals 0. So we need two numbers that multiply to 130 and are negative 130 and add to negative 3. Okay. So we have n minus 13, n plus 10. From here, n equals negative 10. Why is that not possible? Can you have a negative amount of sides? No, so that one's not going to work. Our answer will be n equals 13. And just a reminder, with factorials, n has to be a natural number. Negative